So good afternoon. Good afternoon, Professor Sharma.
Good afternoon. Good afternoon.
Hope everything is fine.
Yes, everything is perfectly fine. Thank you.
So I think we can start with the session. So dear participants, we welcome Professor Pawan Sharma again for the second day, for the second session. And without any delay, I request Professor Pawan to please start his lecture. Students are joining, and Yatin, please tell them to join quickly. Okay?
Yeah, sure, ma'am.
Okay. So maybe I can start. Would you please once let me know that if my slides are clear?
Yes,
Clear
sir.
slides are clear.
Yeah, so means everything is in. And I would request host if you can just mute this joining sound. There is an, you see at your end, you have a control that when someone joins or leaves, it should not be as you are seeing this video. No?
Yeah, done, sir, done.
Yeah.
I have changed it. Yeah.
Okay, so I hope that most of you who have joined today are continuing from yesterday. So yesterday we came to a level where we discussed about this concept of shielding and de-shielding, where we said that we started with a bare nucleus, and then we reached a stage where we said that in the story we found out that if nu is equal to gamma b0 by 2 pi, then everything is constant because magnetogyric ratio depends on the nuclei. So all protons would have the same magnetogyric ratio. All carbon-13 would have same. So B0 applied magnetic field is same. And pi is also constant. So then that way we should have got only one signal. So that is when in the story we started asking for our questions that where did we falter? And we found out that we are dealing only with the nuclei and we forgot to take into account the contribution of the electrons, circulating electrons. And I told you that for the understanding of NMR, you should always think about that whenever you put some nuclei in an external magnetic field, we would always take the direction of the applied magnetic field from the bottom to the top, and the electrons would start to circulate under the influence of the applied magnetic field, and the circulating electrons would generate an induced magnetic field. They would generate another, means their own magnetic field, what we call as induced magnetic field, whose direction would always be opposite in the middle. Let us say that this ring is representing the direction of circulation of electrons. I gave you the animation that ultimately you see the electrons motion is different, but for the purpose of understanding, you can think that this is the ring around which the electrons are circulating. So when I apply an external magnetic field, let us say that the direction of the applied magnetic field is from the bottom to top. So the electrons would start circulating like this, perpendicular to the direction of application of the applied magnetic field. And then these circulating electrons, they would generate a magnetic field of their own, which would always be opposing in the middle. So in the middle of this ring where it is circulating, at the middle of the ring, like this finger is telling the direction. So that is the induced magnetic field. And based on that, we said that the effective magnetic field felt by the nucleus would be less than would be a combination of the applied magnetic field and the combination of the applied magnetic field and the induced magnetic field. So for shielding, the induced magnetic field would be in the opposite direction. For de-shielding, it would be reinforcing, it would be in the same direction. So that is why we said that our definition, our basic NMR equation, nu is equal to gamma B0 by 2 pi. Now it got changed to nu is equal to gamma B effective by 2 pi, where B effective is equal to B0 minus B prime for shielding, and it is B0 plus B prime for de-shielding. So we can say that nu is directly proportional to B effective. So that means although the applied magnetic field B0 is the same, but still the effective magnetic field felt by different nuclei in the same molecule they are not same. So B0 is the same, but B effective may not be the same. And that explains that why do we get signals at different positions for different protons. And the number of NMR signals is equal to the number of different types of protons. So we can say that in the absence of the induced magnetic field, or in the absence of shielding and deshielding, we would have got one position for all the NMR, for all the protons. All hydrogens should have come at the same position. So we can say that due to the shielding and deshielding, there is a shift in the absorption frequency. Right? Nu is equal to gamma B0 by 2 pi. The moment you replace B0 by B effective, and I explained why. So you can say that there is a shift in the absorption frequency due to shielding or deshielding. And why there is the shift? Why the shielding and deshielding? The shift in the frequency depends upon the chemical environment. Electronegative hai, electropositive hai. So first thing, there is a shift in the absorption frequency due to shielding and deshielding. And the shift in frequency depends upon the chemical environment. So that is why in our story, we named it as chemical shift. So we said that is why we are calling it as a chemical shift. That the influence of the chemical environment on the absorption position of any proton, any nuclei. So how do we define the famous definition that is given in all books? That the difference in the absorption position of a particular proton from the absorption position of a standard or reference is called the chemical shift of the particular proton. Reference is always necessary. For example, if you have to measure the distance, let us say between Amritsar and Ludhiana, so you cannot measure it from GNDU. Somebody cannot measure it from another place. So there would be a landmark, let us say your bus stand. So there would be one reference from where you would measure all those distances. So like this, here also the difference in the absorption position of a particular proton from the absorption position of a standard or a reference is called the chemical shift of the particular proton. And all undergraduate students, they read that we use TMS, tetramethylsilane, as the reference compound, as the standard for measuring the chemical shift. But why do we measure, why do we use TMS? You see, there are many reasons. Some are facts and some are reasons. The fact is the silicon is more electropositive than carbon, but the significance of it being more electropositive is that because silicon is more electropositive, due to that, the electrons are pushed more towards the methyl. So the electrons are pushed more to, because silicon is more electropositive than carbon. So they are pushed to, the electrons are pushed towards the carbon, and due to that, the 12 electrons, they are very highly shielded because the electrons are being pushed. The second is the 12 protons in TMS are magnetically anisotropic. Magnetically isotropic. That means they are magnetically equivalent. How does it, what is the significance of it? The significance of it is that it would give a very, very sharp and intense signal at very low concentrations. Third fact is that TMS is highly volatile. So it is volatile. That means we don't want to lose our compound, our sample. So that means after our NMR is done, we can simply evaporate TMS out of it and we can get our pure compound back. And number 4, TMS is chemically inert. That is also very important. You can get a very nice reference compound, but that may be reacting with so many compounds. So with the result that ultimately the NMR of your sample may not be the NMR of your sample. That can be the NMR of the product of the reaction of your sample and your reference. So that is also an important characteristic, and TMS is chemically inert, and it is miscible with most organic solvents. That's also very important, because if it is not miscible, then we won't be able to use it as a reference for very many studies. And the chemical shift is basically, it is measured in hertz. So the actual units of chemical shift are hertz. But by convention, now what we have done for our own convenience and to make the things simple, we are reporting it in ppm, and it is denoted by the symbol delta. So the actual units for chemical shift are hertz. That are hertz. But for our convenience, we measure it in ppm, and it is denoted by the symbol delta. And delta in ppm is equal to 10 to the power 6 into nu minus nu TMS divided by nu 0. So nu is the, that means the frequency of you see the shift or the frequency of the sample nuclei. Nu TMS is that of the TMS, and nu 0 is the operating frequency of the machine. Remember that chemical shift depends upon the operating frequency. The chemical shift depends upon the magnetic field applied. But the chemical shift using this equation, that means chemical shift in ppm, is not dependent on the magnetic field. And it is convenient to express it in ppm where TMS is set to 0. So here two things I'll again highlight for the benefit of my younger audience. The number one, chemical shift depends on the magnetic field, but when we report it in ppm, so by this empirical relationship, we have converted it, we have made it independent of the magnetic field. So that means the value of, let us say, benzene would stay the 7.27 ppm, doesn't matter, I record it at 100 megahertz machine, 200 megahertz machine, or 1000 megahertz machine. So that is in ppm. So it is dependent. In hertz, it would be dependent, but we made it independent. That is one thing. Second thing is, most of the time students say that the TMS absorbs at 0, TMS resonates at 0. No, it's not like that. Wherever TMS absorbs, we set it to 0. So we set the TMS signal to 0, and it is not that the TMS absorbs at 0. So now we can we can understand the concept of shielding and de-shielding. So more the shielding, more the upfield shift, lower the delta value, more the de-shielding, more the downfield shift, higher the delta value. I always ask my students to remember it as DDH, de-shielding, downfield, higher delta. So opposite would also be true, shielding, upfield, lower delta. So we have this normal spectrum is from 0 to 10, the 1H NMR spectrum, 0 to 10. So 10 side is high frequency, 0 side is low frequency, or 10 side is high field, 0 side is low field. So that means now from simple nu is equal to gamma V0 by 2 pi, we came to many signals, we came to shielding and de-shielding. From shielding and de-shielding, we introduced the concept of chemical shift. Now, if we have the chemical shift and the range is from 0 to 10 or 0 to 15, then there must be some factors affecting the chemical shift. So what are the factors affecting the chemical shift? The first factor is the electronegativity or the inductive effect. We know that the electronegative atoms, they have an affinity for the electrons. That means they tend to withdraw electrons towards itself. More electronegative the atom is, the stronger is this affinity. For example, let us compare two cases where a hydrogen is attached to carbon or oxygen. Now, because carbon is less electronegative than oxygen, so what would happen? That the bonding electrons of the carbon-hydrogen bond, they would be more towards hydrogen as compared to the bonding electrons of oxygen and hydrogen. They would be more towards the oxygen because oxygen is more electronegative. And that you can see from the redness around this oxygen. You see in this electron map, you can see that it is a little more red. So that means the redness is showing that the electrons have been pulled away from the hydrogen towards the oxygen. So that means there is more electron density on oxygen as compared to electron density on carbon, or there is more electron density on the hydrogen that is attached to carbon as compared to the electron density around H, or around the hydrogen attached to oxygen. So we know that electronegative atoms or electron withdrawing functional groups, they are considered to be de-shielding. All books write it, that electronegative atoms or electron withdrawing functional groups, they are de-shielding, but in fact they are not de-shielding, they are less shielding. And electropositive atoms or electron donating functional groups, they are considered to be shielding. So the electronegative atoms, simple, when they are withdrawing groups, when they are withdrawing electrons through inductive effect, they are not de-shielding, they are simply less shielding. But by convention, we are using this term that they are de-shielding. Say, for example, you can see here that if I look at these methyl protons, CH3 hydrogens, and the signal for the CH3 hydrogens, then we can see that there is a clear trend which explains, which is on the basis of that higher the electronegativity, higher the de-shielding. In fact, it is not higher the de-shielding, it is lesser the shielding. But the books write it, so I don't want to confuse you. So higher the electronegativity, higher the de-shielding, higher the chemical shift. That means now if you look at the ppm values, the chemical shift values for these three hydrogens of the methyl, so you can see that as the electronegativity of the attached atom or group increases, you see the chemical shift in ppm also increases. Whereas for TMS, we set it to 0. So I would say that for the young learners, for the new learners, it is better that instead of learning that higher the electronegativity, higher the de-shielding, I think the best way to learn it is by saying that the higher the electron density around a proton, higher the shielding. Lower the electron density, lesser is the shielding. So higher the electron density around a proton, higher the shielding, lower the chemical shift. And this electronegativity, it also, we know that it dies down with distance. So greater the distance of electronegative atom or group from a particular proton, smaller is the de-shielding effect on it. For example, you see if you look at the propane and the nitropropane, so you see now nitro is strongly electron withdrawing. So that means it is withdrawing the electrons towards itself. So that means the electron density on the CH2 protons is much less because of the presence of the nitro. So with the result that it is de-shielding. In fact, it is lesser shielding. So de-shielding, downfield, higher delta. So you can see that 4.3 to 1.2. Why? Because the distance of these CH2 protons is more as compared to these CH2 protons from the nitro group. The impact is of the nitro group. Similarly, you can see here that CH3Br, RCH2Br, RCH2CH2Br, RCH2CH2Br. So we are recording the protons which are attached to the red carbons. So here also you would see as the hydrogens, they are moving away from the bromine, the electronegative atom. So you can say that the chemical shift values are decreasing. So we can say that electronegative atom, as the inductive effect dies down with distance. So we can say more the distance from the electronegative atom, smaller would be the de-shielding effect. And the de-shielding effect of electronegative substituents is cumulative. Say for example, here we have methane. So methane absorbs at 0.23. Now if I replace one of the hydrogen with a chlorine, so now you see it is strongly electron withdrawing. So the chemical shift moves from 0.23 to 3. Now if I replace one more hydrogen, so now I have two electronegative atoms, two electronegative chlorines here. So the effect of the de-shielding effect of the electronegative substituent would be cumulative. That means it would be additive. So from 0.23 it comes to 3. When I replace one more hydrogen with chlorine, it jumps to 5.28. When I replace another hydrogen with chlorine, it jumps to 7.24. And when I replace another hydrogen with chlorine, so then it should be higher than 7.24, but unfortunately there is no hydrogen left. So the CCl4 is NMR inactive because there is no hydrogen in it. So that is the one factor. So the major factors affecting are only electronegativity and the anisotropy. All other are, you can say that they are manifestations of these two, you can say the factors. So the second factor is the hybridization effect. Now, if we try to understand hybridization in terms of electronegativity, so we know that the higher the S character, higher is the electronegativity. So we can say that the electronegativity of sp orbitals is the highest as compared to sp2, as compared to sp3. So that means the expected order would be that sp would be less than sp2 and that would be less than sp3. But the actually observed order is sp2 less than sp3 and that is less than sp3. So that means now sp is not coming at its normal position. So it is shifting. And why it is shifting, we'll get its answer in the third factor, and that third factor is the anisotropic effect. So electronegativity is one important factor, anisotropic effect is the second important factor. So anisotropic effects, we also call these as space effects or pi electron induced field effects. So first of all, what is anisotropy? Now, I'm sure that when you study it in class, then many times the students and even the teachers, they would try to give you examples from the crystals and crystal defects. And that becomes very difficult for the students to understand because isotropic and isotropic, these are very simple concepts if we try to explain these to students. So what is isotropic? Isotropic simply means operating equally through space. And isotropic means operating non-uniformly through space. For example, I'm sitting in this room, all doors and windows are closed. So that means I'm presuming that the air inside it is not getting circulated. AC is not on, fan is not on. So I can say that air is isotropically distributed in the room where I'm sitting. Whereas on the other hand, I have a tube light in front of me. So there is more light in my front as compared to my back. So light is anisotropically distributed in the room. So that is anisotropy, nothing more than that. So isotropic and isotropic. Now, what are these anisotropic effects? Now, there are some effects which can actually produce a magnetic field that reinforces B0. And one of these effects is called ring current. If you remember, when I introduced to you the concept of shielding, at that time I said that if the induced magnetic field opposes the applied magnetic field, then it's a case of shielding. And then I said, if the induced magnetic field somehow reinforces, because I told you induced magnetic field would always be opposing the applied magnetic field, but in the center. So when induced magnetic field would always be opposing the applied magnetic field in the center, then how come this induced magnetic field be aligned to the applied magnetic field? But at that time I told you, if somehow the induced magnetic field is aligned with the applied magnetic field, then I would say this is a case of de-shielding. So one of these effects you see is called the ring current. What is the ring current? Say for example, if we have this benzene, then the atoms of this skeleton, they are sp2 hybridized, and there is a p orbital available on each carbon. For example, this is shown a p orbital. And these p orbitals, let us say that this is benzene. So p orbital, p orbital, p orbital, p orbital, everywhere, 6. So p orbitals on adjacent carbon atoms, they can align and can produce a pi system. They can produce a circulating pi system at the top as well as at the bottom. And organic containing compounds containing these pi systems, they permit a type of electron motion which is termed as ring current. Say for example, if you see here that here is a mauve color is carbon, and this blue color is hydrogen. So you see 6 mauve colored carbons. So it's a benzene and hydrogens. So each of these carbons, they are having a p orbital. So these p orbitals, they align themselves at the top and at the bottom. So that is called the ring current. So now we are having circulating electrons at the top as well as at the bottom. We call it as ring current. And what did I say? That if this is the ring of electrons which is circulating, so induced magnetic field would always be opposing in the middle. So that is why this is the direction from bottom to top of the applied magnetic field B0, but the induced magnetic field is opposing in the middle. So that is coming in the opposite direction. We can see it in another diagram. Let us see here. So here you see this black carbon is having the p orbitals. And so all these p orbitals, they make a ring current. And this arrow is pointing the direction of the induced magnetic field, that is from top to bottom against it. And this B0 is the direction of the applied magnetic field. So that means in this case, if suppose that this hydrogen, which is from which is from carbon to hydrogen and pointing outwards, if suppose that our chemistry gets so advanced that we can take this hydrogen inside it, that means this hydrogen is not pointing outward, but it is pointing inside the benzene ring. Suppose imaginary situation that our chemistry develops so much that we can put this hydrogen inside, then you can imagine what would happen. That this hydrogen would be directly in the range of, in the line of the induced magnetic field, which is a strong magnetic field which is opposing at the middle. So which is at the opposite direction. That means this proton, if it is in the middle, would be strongly shielded, right? And this we can see by cutting it into half. So if this CH is inside, so H would be somewhere here. So that means the induced magnetic field would be opposing the applied magnetic field if the hydrogen is here. But where is the hydrogen? The hydrogen is outside. And as you know that the magnetic lines, they are elliptical, they are cyclical. So they are opposing in the middle, but when these magnetic lines go back, then you can see that these hydrogens, the hydrogens of the benzene ring, they are located, pre-organized, located in the return portion of the magnetic lines. You're understanding? The aryl hydrogens are located in the return portion of the ring current magnetic field. And that is why the B0, which is opposing the applied magnetic field in the middle, is reinforcing the applied magnetic field when it reaches the hydrogens, which are attached. You see here, 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 and here. So it reinforces because they are located in the return portion. So now at the hydrogens of the benzene ring, the induced magnetic field and the applied magnetic field, they are in the same direction. If they are in the same direction, that is a first true case of de-shielding. So this is a case of de-shielding, that induced magnetic field is reinforcing the applied magnetic field. And that is why you see methane absorbs at 0.23, whereas benzene absorbs at 7.27. Ethane absorbs at 0.90, whereas toluene, methyl protons of toluene, they resonate at 2.34. So this is a strong anisotropic effect from 0.23 to 7.27. So there is a jump of almost about 7 ppm. So this is anisotropy. Another thing, please do not, if there are some teachers, please do not teach this anisotropy by drawing those Damru diagrams where saying this is positive space, this is negative space, because I'm sure that some of the students would find it difficult to cram, and in the exam, when they have to remember, they might be confused. Once if they are confused between positive and the negative domain, it would be very difficult. Whereas if we understand it in terms of the induced magnetic field, and induced magnetic field would always be opposing in the middle, I think that the concept would stay with the students for life. So this is anisotropy. Let us look at the anisotropic effect in case of ethylene. Now here you see we have 2 electrons. In case of benzene, we had 6 electrons, so we had a large ring current. But here you see in this case, let us say that this is ethylene, this is carbon, this is carbon. So 1 p orbital here, 1 p orbital here. So what can happen? That these 2 p orbitals can align at the top as well as they can align at the bottom. So with the result, now there is a circulating ring current at the top and a circulating ring current at the bottom. And what did we say? That the induced magnetic field due to these circulating electrons would always be opposing in the middle. So the induced magnetic field would be opposing in the middle. But again, you see where there are hydrogens of this, the hydrogen is here, the hydrogen is here. So at that position, now the induced magnetic field is in the same direction. So that is reinforcing. So that is why you see in case of ethane, ethane protons absorb at 0.90, whereas ethylene protons, they absorb at 5, delta 5. So there is a big jump. Why there is a big jump? We cannot explain it on the basis of electronegativity because there is not much difference here. It is only sp3 and sp2, but we cannot explain it on that basis. It can be explained only on the basis of anisotropic effect. Now if you replace the CH2 with an oxygen, so in the case of aldehydes and ketones, now the effect would be multifolded because there would be, number one, there would be anisotropy. Number two, there is oxygen in place of CH2. So oxygen is electron withdrawing. So it will be withdrawing electrons towards itself. So that means the effect would be cumulative due to anisotropy as well as due to electronegativity. So that is why you would see that in case of aldehydes and ketones, the deshielding effect is so much that the aldehydes absorb at about 9 to 10. So strongly deshielding. Now, so that means now why the jump is here only of about 4 or 4.1 ppm, whereas the jump was of 7 ppm in case of benzene. So we can say in case of benzene, the ring current was due to 6 electrons, whereas in case of ethylene, the ring current is only due to 2 electrons. So, but in that case, when we come to ethylene, acetylene. Now, in case of ethynes or acetylenes, now you see again we have carbon-carbon. We have a p orbital like this, perpendicular, let us say, and another set of p orbitals perpendicular to it. So let us say that the y-axis and x-axis, both axes has the p orbitals. So with the result, what can happen? That we can assume that now there are 4 pi electrons. So benzene has 6, ethylene has 4. So ethylene has 2 and acetylene has 4. So in that case, we'll expect that the acetylene protons should absorb somewhere between 5 and 7.27 because now we have more than 2 electrons here for the ring current. But in actual practice, they absorb between 1.8 to 20. Now, why it is so? Because as I said that there is one set of p orbitals lying in the, let us say, y-axis and another set is lying in the x-axis. So with the result, what can happen? There can be one ring current here, one ring current at the bottom, one ring current at the front and one ring current at the back. So this is one possibility. But now you see, because there are electrons here at the top, at the bottom, at the front and at the back. So with the result, what happens? That electrons try to have a path of least resistance. They try to circulate in such a way that they do not have to do much effort. So instead of circulating in 4 rings, they start circulating around this carbon-carbon spindle. So now you see the circulation becomes like this. So with the result, now what happens? That there is a circulation of electrons. And we said, whenever we apply induced magnetic field, circulation of electrons aligns itself perpendicular to the direction of applied magnetic field. So with the result, in case of acetylene, now because the electrons are circulating around it like a cylinder, so it moves vertically. And now you see the induced magnetic field is opposing in the middle. So in case of ethylene, hydrogens were in the return portion. That is why they were de-shielded. But here now they are in the middle. So they are in the shielding zone. So because they are shielding, so that is why they do not absorb above 5, but they absorb at 1.8. Whereas in case of ethane, you see we have at 0.9. Here we have shielding and still it absorbs at 1.8. So there can be one question coming to your mind that if it is in the shielding zone, then the value should come less than 0.9. So why it is coming at 1.8 or 2? I think that you should think on your own, and I'll be happy to answer in the end if still you have a question. And the fourth factor is the hydrogen bonding. This is one factor which is not very well taught to the students and not given in very many books. But if we say hydrogen bonding, this is also an impact of electronegativity. Because a hydrogen atom that is involved in hydrogen bonding, what would be the impact? The electronegativity impact. So electron density would be away from the hydrogen atom that is involved in hydrogen bonding. With the result, the electron density would be less. Electron density would be less. So that means lesser shielding or de-shielding. So it will get de-shielded and would absorb at a higher delta value. So stronger the hydrogen bonding, more de-shielded. That means the higher the chemical shift. We can take it as a very beautiful example. Here, if you see, I have two NMRs here. One is that of salicylaldehyde and the another is that of ethanol. Now you see, in case of salicylaldehyde, the OH and carbonyl, they are predisposed in such a way to have a very strong hydrogen bonding. And this is intramolecular hydrogen bonding. Whereas in case of ethanol, there would be intermolecular hydrogen bonding. Now, I know that if you study IR also, especially the research scholars and the master students, that you study in great detail in IR that how to differentiate between inter and intramolecular hydrogen bonding. But you do not study it in NMR. Whereas I consider that NMR is a much more powerful tool to study the intermolecular and intramolecular hydrogen bonding as compared to the IR. For example, here you see salicylaldehyde has intramolecular hydrogen bonding, ethanol has intermolecular hydrogen bonding. So let us say that we want to differentiate which one has intermolecular, which one has intramolecular. So what we can do, we can record their NMR spectrum as neat or in very concentrated solution. After that, what we can do, now we can rerun their NMR spectrum, but in a very dilute solution, let us say 5%. And we simply compare the two NMRs. So you see, if you compare the NMR of salicylaldehyde when it is taken as neat and when it is taken as 5%, so you can see there is no change, no shift in the position of the OH. It is at the same place. Whereas in case of ethanol, now you see when I dilute it, I see a change in the position of the signal for the OH. And that is the very simple tool. So that means if I record the NMR spectrum of a compound suspected to be involved in hydrogen bonding as neat or as a very highly concentrated solution, and then as a dilute solution, and if the position of the hydroxy group, position of alcoholic hydrogen changes in that in the two NMR spectra, then it is a case of intermolecular hydrogen bonding. If it doesn't change, then it is a case of intramolecular hydrogen bonding. So it's an excellent tool in the hands of the chemist to differentiate between intermolecular and intramolecular hydrogen bonding, which is not given in many books and which is not being taught to that level where I think that it should be taught, because it's really a very simple tool. So the next stop or next chapter in our story is that up to now we say we are comfortable in saying that a number of NMR signals is equal to number of different types of protons. And chemical shift data tells us what kind of protons we have. That means, what is the environment of the protons? Is there electronegative atom or group or electropositive atom or group? The next question comes that can we find the number of protons? Of course we can find. Why we can find? Because what we do in NMR, that we have aligned nuclei in the aligned state. So what we do, we add energy. So all of these nuclei, all of these hydrogens, they get excited to the high energy state. And from the high energy state, they release energy and they come back to the ground state, the low energy state. So when they come back to the low energy state, they release an amount of energy and we measure that amount of energy released. So suppose that if one hydrogen, when it comes back to the ground state, if it releases 2 units of energy and the energy measured in one experiment is 6 units, so I can say that there are 3 hydrogens which are in this group, right? And if it is 8 units, 4 hydrogens, 4 units, 2 hydrogens. And this amount of energy released, this affects the size of the peak in NMR spectrum. More the hydrogen atoms, bigger the peak. Please remember, I'm writing bigger. I'm not writing taller. I'm not writing more height, right? I'm writing bigger the peak. It is deliberate. Why? Because we are not comparing peak heights. We are comparing peak areas. So area under a peak is proportional to the number of contributing protons. And area, as you can say, it's a direct consequence of the amount of energy released. So we do not compare peak heights, but we compare the areas under a peak. So area under a peak is directly proportional to the number of contributing protons. Say, for example, if we have methanol, then we would have 2 types of protons, methyl, CH3, 3 protons of one kind, 1 proton of the other kind. So we'll have 2 signals, and the signal for CH3 is larger and stronger than OH. For example, you see here CH3 and OH, and but we cannot simply compare the peak heights. It is the area under the peak that is important. Now, earlier, you see, in earlier times when I started my research, we used to have these on graph. So at that time, you see, you have to count the number of squares of the graph to find out the integration. But nowadays, you see, the computer does it all. It measures the area under the peak and then plot it as a vertical line. So that means it is converting the area into a linear unit, and then we are comparing the heights of these lines. In more modern, you see the standard NMR instruments, now even the line is also not plotted, but only you see the area. That means their relative ratio is printed at the bottom. So say, for example, here in this case, this is 20 mm and the 7 mm. So that means the areas under the peak is in the ratio 20:7, which is 3:1.05, and whole number ratio is 3:1. So that means if there are 3 protons here, then 1 proton is here. So nowadays we have automatic integrators. And with that integrator, it is telling me that the areas are in the ratio of 3:1, right? But please remember one very, 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 very important thing. Integration of peak areas, it gives us the relative proton count and not the absolute proton count. That means 3:1 ratio is telling me that if there are 2 sets of protons in my compound, and if one kind of protons are 3, if one kind of protons are 3, then the other are 1. But it is not telling me that absolutely there are 3 protons and 1 proton, because I'll get exactly the same integration, exactly the same NMR spectrum if I have 6 protons of one kind and 2 of the other kind, or I have 9 protons of one kind and 3 of the other kind. So it gives me the relative proton count and not the absolute proton count. But then the next chapter comes about the splitting of signals. We know that we do not get signals because we came from, in the story, we came from a single signal. Then we came to be effective and we said we'll get many signals. But we did not talk about the multiplicity of the signals, that whether the 3 signals in ethanol that we obtain, would those be singlets? Right? 3 signals, because now we know how to find out equivalent and non-equivalent protons. So I can say there are 3 types of protons in this in ethanol, 3 protons of one kind, 2 of one kind, and the 1 of the other kind, third kind. So that up to now what we studied, it would tell me that we should get 3 peaks. But would we get 3 singlets? Let us say that I showed you this cartoon earlier. Would I get 3 singlets like this? CH3, CH2, OH. We know that we do not get singlets, but in fact, actually we get multiplets. For example, here you see a triplet for the methyl, a quartet for the methylene, and singlet for the OH group. So why do we get these multiplets? That in our story, we still couldn't understand. So that means when we get these data, this type of questions in the story, it forces us to think that what we are leaving. We started with a bare nuclei. Then we added the contribution of the circulating electrons of that very nuclei. But we thought that maybe there is 1 proton, 1 hydrogen which is isolated. Earlier we thought there is only 1 nuclei. But here we did not take into account the impact of the nuclei which are nearby. Because you see the energy levels of a nucleus, they would be affected not only by the induced magnetic field generated by itself, not only by the applied magnetic field, but they will also be affected by the spin state of the nuclei nearby. That we did not take into account. So the energy levels of a nucleus will be affected by the spin state of the nuclei nearby. and the two nuclei that show this relationship, that means where they are affecting the energy levels of each other, they are said to be coupled to each other. Coupled to each other, and coupling is always through bond. Say for example, this is a 2-bond connectivity, 1 bond, 2 bond. This is a 3-bond, what we call as a geminal and the vicinal. So coupling is through bonds. So that means why do we get splitting? We get the splitting because the energy levels of a nucleus, it would always be affected by the spin state of the nuclei nearby. Let's take an example. Let us say that I have this you see a different kind of compound. The only purpose of myself showing this compound is that I want to show that there is only one proton here, HA. It is listed with HA. So if there is only one proton here, so what would happen? That there would be the applied magnetic field, then there would be induced magnetic field due to the circulating electrons. So the B effective is represented here as BA. So BA already is taking into account the contribution of the applied magnetic field and the contribution of the induced magnetic field. So BA is B effective. So due to this, there would be one particular energy difference between the low energy state and the high energy state, and triation can take place. That means now this is the aligned state, this is the opposed state. So there would be an energy difference between the aligned and the opposed, and when the radio frequency energy would be matching the energy difference between this aligned and the opposed states, so resonance would take place and we'll get an NMR signal, we'll get a singlet. But now imagine that there is one more proton HB nearby. Now when HB would be nearby, so still you see in this diagram, please do not look at both these. Just imagine that there is A. Now I am observing proton A. So A is aligned and the opposed state. Now, but what would be the impact of the neighboring B, neighboring HB hydrogens? Now the hydrogen B's field would also be impacting the energy levels of A. Now when the hydrogen B's field is aligned, say for example, you see A is aligned, A is opposed, but hydrogen B, it has a small magnetic field, and this can either be aligned or can be against the external magnetic field. Now when hydrogen B's magnetic field is aligned against B0, you see this is aligned, HA aligned, HA opposed, but here B aligned, because I'm looking at HA, we are observing HA. Now what is the impact of HB? HB's hydrogen field can be aligned against B0. Now when it is aligned against B0, hydrogen A would be shielded because now it is aligned against the applied magnetic field. And this BA is the effective magnetic field felt by HA in the absence of HB. So this is already B effective of HA. But now when I have nearby nuclei HB, which is opposing, which is aligned against the B0, then what would happen? There would be a shielding influence of this B, because the magnetic field of B is aligned against the applied magnetic field. And if the magnetic field, when the hydrogen B's field is aligned with the applied magnetic field, then what would happen? In that case, the HA would be deshielded, right? When HB is opposed to the applied magnetic field, it would have a further shielding effect because the direction of its magnetic field is opposing the applied magnetic field. And when HB's magnetic field is aligned with the applied magnetic field, then there would be a deshielding influence because now you see the effective magnetic field felt by HA would be higher. So that means we will have some nuclei shielding and some nuclei deshielding. And if you remember the population difference, we said that there is almost the same population in two spin states. So there was a difference of only let us say that the 16 nuclei or 64 nuclei. So in 2 million, 16 is not a big difference. So that means B aligned or B opposed would be almost in the same population, the same number of HB nuclei. So with the result, now what would happen? HB would split HA. Half of the HA it would take to the shielding zone. It would shield the HA, and the other half of HB, which is aligned with the applied magnetic field, it would take this HA to the deshielding. So half of the signal of HA would be shielded, half of the signal of HA would be deshielded. So with the result, HB would split HA into a doublet, and intensity of these two lines would be of the doublet would be equal 1:1, because the population density of HB in the aligned and the opposed state is almost the same. So instead of singlet, now we are getting a doublet, and the frequency of separation between these two lines is called J, is denoted by J, and it is called the coupling constant or the dipolar coupling constant. And please remember, coupling is reciprocal. Reciprocal means if HB splits HA by 10 Hertz, then HA would also split HB by 10 Hertz. It is equivalent to that you invite your friend on your birthday and your friend gives 501 rupees. So when you go back to his or her birthday, you also return the 500, give them 501 rupees. So coupling is reciprocal. If HA splits HB by 10 Hertz, HB would also split HA by the same amount, that is by the 10 Hertz. So coupling is reciprocal. And I told you that the chemical shift is dependent on the strength of the applied magnetic field. It is dependent on the strength of the applied magnetic field, but coupling constant is independent of the applied magnetic field. Chemical shift is recorded in Hertz, but reported in ppm. But coupling constant is reported in Hertz. It's never reported in ppm. Please remember, chemical shift is also, basically it is measured in Hertz, but it is converted by that semi-empirical relationship into ppm. But coupling constant is always reported only in Hertz. We can also explain it if your color coding you don't understand. We can also explain it by the directions. So you see this is HA top, bottom, HB bottom, bottom. So opposed, HA top, HA bottom, HB top, HB top. So that is de-shielding. So in that case, you see that's the same. It doesn't matter whether you use the arrows or you do the color coding. Similarly, let us say if I have 3 HBs neighboring to HA, what would happen? You know that HB would still be a doublet. That means split into 2 lines, but HA would be a quartet. Why HA would be a quartet? Because now you see I'm observing HA. So HA aligned, HA against. But now I have 3 HB. So these 3 HB, they can have 4 possibilities. All 3 HB aligned. So for example, see aligned here, aligned here. So when they are aligned, so what would happen? Strongly de-shielding, very, very strongly de-shielding. Second possibility is all 3 opposed, all 3 HB opposed. That will be a case of strongly shielding. So that means 2 lines will get, one would be very strongly shielded, one would be very strongly de-shielded. Now, the third possibility can be out of the 3, 2 can be aligned, one can be opposed. Now, if you label them as X, Y, and Z, so you can say 3 HB labeled as X, Y, and Z. So here you see the X is opposed, Y and Z are aligned. Here Y is opposed, X and Z are aligned. Here Z is opposed, X and Y are aligned. So that means this possibility where 2 of them are aligned and 1 is opposed, it can take place in 3 ways. There are 3 possibilities. So that will be, now you see 1 aligned, 1 opposed are cancelling each other. So 1 aligned is the net effect. So that would be de-shielding. So we have a strongly de-shielded signal. We have a de-shielded signal. That means less de-shielded as compared to the strongly de-shielded. Similarly, there is another possibility where instead of all 3 opposed, we have 2 opposed, 1 aligned. And this also has 3 possibilities. So we can have again 1 and 1, 1 aligned, 1 opposed get cancelled. So we'll have a shielding. So we have strongly de-shielded, de-shielded, shielded, and strongly shielded. So what would happen? Now we'll have a quartet. So that signal HA, which is a singlet in the absence of HB, 3 neighboring HB, now that signal of HA, due to the presence of 3 HB, it splits into 4 lines, and the intensity of these lines would be 1:3:3:1. Why 1:3:3:1? Because strongly shielded and strongly de-shielded, they would have only 1 possibility, whereas you see the 2 aligned, 1 opposed, or 2 opposed, 1 aligned, they would have 3 possibilities each. So they have 3 times more probability. Because of that, now we have the relative intensities of these lines would be 1:3:3:1, right? And so likewise, suppose we have 2 HBs close to HA. So what would happen? How would HB appear? HB would still appear as a doublet, and HA would appear as n+1, you can say as a triplet. And what would be the relative intensities? You should try to draw such a diagram, and you should try to find out the relative intensities. And as you know, the relative intensities would be 1:2:1. So that means now we have come to a stage where not only we are getting multiple signals, but the signals can be multiplets. They need not necessarily be singlet. They can be doublet, triplet, quartet, quintet, sextet, septet, anything, or simply a multiplet. So, but would all hydrogens couple or split each other hydrogen present in the molecule? No, there are certain conditions for spin-spin coupling. The first condition is that the hydrogens have to be suitably close to each other. Suitably close, generally up to 3 bonds away. So we can have 2-bond coupling, what we call as the geminal coupling. We can have 3-bond coupling, what we call as the vicinal coupling. 1 bond, 2 bond, 3 bond. So we can have 3 bond. That means that first condition for spin-spin coupling is that the hydrogens have to be suitably close to each other, generally up to 3 bonds away. That does not mean that the 4-bond coupling is not observed or 5-bond coupling is not observed. That is also observed, but generally up to 3 bonds, the coupling is always, not always, most of the times observed. Even 3-bond coupling is also sometimes 0, so you don't see it. But still you see the generally 3-bond coupling is observed, 2-bond and 3-bond, but there can be long range coupling also. So second condition is they should have different chemical shifts. That means equivalent protons, they do not split each other. They do not couple with each other. Only the non-equivalent protons, they couple with each other. Third one is that we can find out what would be the multiplicity of the signal by n+1 rule, where n is the identical number of identical protons in the neighborhood. For example, CH3, CH2, Br. So CH3, what would be the multiplicity of CH3? That would be n. N is the number of neighboring hydrogens. The neighboring hydrogens are 2. So 2 + 1, triplet. And the multiplicity of CH2 would be 3 + 1, 4, quartet. So, and we follow the n+1 rule. And so that means if the number of neighboring hydrogens are 0, we'll have a singlet, 1, doublet, triplet, quartet, quintet, sextet, septet, and so on. And intensities of these lines, they can be predicted by the Pascal's triangle. So singlet, doublet 1:1, triplet 1:2:1, quartet 1:3:3:1. So they can be predicted by the Pascal triangle. But please remember that all couplings are not necessarily equal. Say for example, if we are observing HA and it is having HM on one end and HX on the other end, so we cannot presume that the coupling constant between HA and HM would be the same as the coupling constant between HA and HX. Need not necessarily. And if it is not the same, then what happens? In that case, we get a complicated pattern that we can explain on the basis of a tree diagram. For example, in this case, HA would not show as a triplet because of the 2 protons in the neighborhood. It would show up as a doublet of a doublet. Doublet due to HM and doublet due to HX. And the fifth condition is that the coupling is reciprocal. As I told you, that if HA splits HB by X hertz, HB would also split HA by the same amount, that is by the X hertz. So how do we measure? Do you see coupling constant? You see it is the distance between the 2 adjacent peaks in a multiplet. That is the coupling constant between 2 adjacent, right? That is important. 2 adjacent peaks in a multiplet. And it is denoted by the letter J, and it's measured in hertz and not in delta values. It's not measured in ppm. It's always measured in hertz. And chemical shift is dependent on the applied magnetic field, but coupling constant is independent of the strength of the applied magnetic field. Magnitude of the coupling constant is determined by the number as well as the kind of intervening chemical bonds and the spatial relationship between the protons. But coupling is through bonds. It is not through space. Although the spatial orientation affects the coupling constant, but still the coupling is through bonds and not through space. So how many types of couplings are there? One is the geminal coupling, that is 2-bond coupling. That means the coupling through 2 bonds, as I have shown you earlier, that the coupling between the 2 hydrogens which are on the same carbon. And geminal coupling depends on the HCH angle. For example, this is a geminal coupling between HM and HX. So it depends on the HCH angle and the electronegativity of the attached atoms or groups. And the typical range of geminal coupling for alkanes is from 5 to 20 Hertz. And for alkenes, it is from 0 to 3 Hertz because it depends upon the HCH angle. So for example, here in case of you see this alkene, HMJMX is equal to JGem. So it is a geminal coupling. We can denote it by JGem, or we can denote it by J2, where 2 is a superscript on the left. So Jgem is equal to minus 1.4 hertz. So it can be positive as well as negative. But when we study NMR as a tool, so we do not take into account its sign. So we always consider that it is, we only take its magnitude. Second is the vicinal coupling, that is the 3-bond coupling. That means protons which are separated by 3 bonds on adjacent carbon atoms, and we denote it by J vicinal or by 3J, J3 where 3 is a superscript on the left. And it varies from 0 to 18 hertz. In case of alkenes, that means in the rigid systems, J trans is always greater than J cis. Say for example, JAM is vicinal and JAX is also vicinal. But in rigid systems like in alkenes, J trans is always greater than J cis. So J trans can be from 10 to 18 and J cis can be from 8 to 14 or 5 to 14, depending upon some other factors like the electronegativity, etc. And in case of freely rotating systems, J anti is always greater than J gauche. So for example, HA and HB are anti, whereas here HA and HB, they are gauche. So J anti is always greater than J gauche. So in an oversimplified way, you can just remember it as, for example, J, A and B are trans or more trans as compared to A and B. Although it is chemically, it is not correct. From chemistry point of view, it is not correct. But I'm saying that you can just think that AB is the true representation of the trans. So J anti would always be greater than the J gauche. Say for example, you see in this case, now JAX is J anti, 7.1 hertz, whereas JAM is J gauche, it is 4.4 hertz. So J anti is always greater than J gauche. And as I said, that usually up to 3 bonds, but it doesn't mean that we do not have long range coupling. We do not have more than 3 bond coupling. We do have more than 3 bond coupling, and we call it as the long range coupling. And coupling through 4 or more bonds, that is called long range coupling, and it is very little, usually between 0 to 3 hertz. And the famous example is either the allylic coupling or the aromatic coupling. So in case of aromatic coupling, you see J ortho is always greater than J meta, which is always greater than J para, right? Why? Because the number of intervening bonds increase and going from ortho to meta and from meta to para, right? We must note here that the spin coupling of a proton nuclei takes place through intervening bonding electrons and not through space. This is what I told you, because sometimes somehow the students get confused when we say that the spatial relationship we can study. Yes, we can study, and the spatial relationship is one factor that is affecting the coupling constant, but the coupling is not through space. You can remember it in this way, that suppose we have a big protein which is having a quaternary structure where you see 2 hydrogens which are close in space to each other, but they have 1000 bonds in between. So these 2 hydrogens which have 1000 bonds in between, but they are very close, let us say 2 angstrom, within 2 angstrom to each other, they would not couple each other, because now there are 1000 bonds and the coupling cannot relay through that. So the spin coupling of proton nuclei or other nuclei takes place through intervening bonding electrons and not through space. That is one thing. And second thing is, splitting means coupling, but coupling does not necessarily mean splitting. So if you are seeing a multiplet, you are showing that there is coupling. But if you are not seeing a splitting, that does not mean that those nuclei are not coupling. So if you are seeing a splitting, coupling is there. If you are not seeing a splitting, coupling can still be there. That can be a little confusing, but it can be explained very easily. But I do not have the time today. Within the 2 hours, you see, it is difficult to do justice to it. So what we have learned up to now, we have learned that number 1, the chemical shift data, it would tell us about the kind of protons we have. That means it will tell us about the environment of the protons, right? Say de-shielded, so that is close to the electronegative atom or group. So chemical shift data tells us about the kind of protons we have. The integrals, integration of the peaks, it tells us about the ratio of each kind of proton in our sample. And the coupling tells us about the protons that are near other protons. That means the proton neighbors, hydrogen neighbors that a particular set of nuclei, a particular set of hydrogens have. Say, for example, if I take the case of ethyl acetate. So you see, first of all, how many signals I'll get? I'll get as many signals as I have the type of the number of different types of hydrogens. So I have CH3 one kind, this CH2 second kind, and this CH3 the third kind. So I should have 3 signals, 1, 2, and 3. So I have 3 signals. But now you see what is the chemical shift is telling. The chemical shift is telling me that one signal is at around 4. So it is round about at 4.2. So that means it is close to an electronegative atom or group. And the integration is telling me that 3, 3, 2. So that means that I have 3 types of protons in it, and they are in the ratio 2:3:3. And another thing is that when I measure the coupling, the splitting, I get a quartet and a triplet. And the quartet and a triplet by the, you see the m+1 rule. So that means the quartet is due to 2 protons in the neighborhood, and due to 3 protons in the neighborhood, and triplet is due to 2 protons in the neighborhood. So that means the quartet is arising due to the CH2 in the ester part. And then you see this singlet is due to the methyl group here because there is no hydrogen in the neighborhood. So it will be a singlet. And you see this triplet is due to the CH3 because it is getting split into a triplet due to the presence of CH2 group nearby. So what are the applications of the this 1H NMR spectroscopy or PMR spectroscopy? Number 1, identification of substances. That is the main application. Determination of their molecular structure. Identification of exchangeable protons. That means protons on nitrogen, oxygen, or sulfur. We can identify based on the NMR because these protons, they can easily get exchanged. For example, red alcohol and blue alcohol, their hydrogens can exchange, and the blue hydrogen can be on the red molecule and the red one can be on the blue molecule. So what we can do, we can add a drop of deuterated water, D2O, and with the result, the H would be replaced by deuterium. So when H would be replaced by the deuterium, so we can measure the signal again. We can measure the NMR spectrum again. For example, this is ethanol. In case of ethanol, now you see we have quartet, triplet, and then a singlet due to this OH. Now, if I add a drop of deuterated water to it, so what would happen? I'll have an OD here. If I have an OD here, then I won't get a signal due to OH or OD. So with the result, now instead of 3 signals, I'll have only 2 signals. So that would immediately tell me that I have an exchangeable set of exchangeable proton in my system. If the OH group is not there, let us say instead of that OH, there is a CH group. So then in that case, the third signal would not disappear. Then we can identify, we can monitor reactions based on NMR. Say, for example, if I have this methyl cyclohexene and I treat it with HCl, then there are 2 products are possible, A and B. Now, on the basis of NMR, you see if my A product is there, then my methyl would be a singlet. But if my B product is there, then my methyl would be a doublet. So if A is the product, then you see I'm getting methyl as a singlet. And if B is the product, then I'm getting, if B is the product, then I'll get it as a doublet. Just one second, there is, yeah. So if B is the product, then I'll get a doublet. And NMR has applications in all fields, in chemistry, in physics, and biology. Particularly in biology, you see it, we can use it for 3D structure determination, assess stability, binding studies, protein dynamics, elucidation of structures of biomarkers, NMR of biofluids, in vivo NMR, as well as MRI, with which you all are familiar. So I was given time from 4 to 5, and that is how much, what justice I could do within that time frame. So thank you very much for the patient hearing, and I'll be very happy to take on the queries, as many as you have. Thank you very much.
Thanks, Professor Pawan. Wonderful lecture. And you can see the comments, they are there. Students are really happy. And dear students, now the session is open for the question answers. And Professor Pawan will be happy to have your questions. So you can ask him directly. There is no need to drop it in the chat box. So please ask the questions. We are waiting for your queries.
Yeah,
Professor Sharma, very beautiful. Really well planned lecture. In 2 lectures, you have taught so much.
Thank you. Thank you very much. So participants can unmute themselves and can ask the questions. I'll be very happy to answer.
Yes, Yatin?
Yeah, ma'am, I'm going to YouTube to check some questions there. We have today live streaming also.
Okay, okay. So that question you can ask questions which are on the YouTube, because those people, they will not be able to ask the questions in person.
Good evening, sir.
Yes, Arshdeep.
Sir, I have a question. In 3J coupling constant, that is vicinal coupling constant.
Yes.
If we talk about alkenes, you have said that J trans is greater than J cis. So basic reason for the J trans greater than J cis is steric hindrance or somewhat anything else?
No, it is not the steric hindrance. Basically, you see, I did not, in 2 hours, it is not possible to cover the factors affecting coupling constant, right? So basically, you see in this case, in the case of J trans, you see the overlap. You can say that the orientation means, in simple terms, you can say that the steric hindrance, but it is not steric hindrance. Basically, it is the angle between the 2 hydrogens. So based on that, basically, in case of vicinal, you see we talk about you see the Kaplus correlation curve. It is the dihedral angle which determines what would be the coupling constant value. So that the vicinal coupling constant is the highest when the dihedral angle is either 180 and then slightly lower when it is close to 0. We call it as the anti-periplanar and syn-periplanar. And if you remember, I said that the coupling means, I said that even sometimes the 3 bonds, the protons which are related to each other by 3 protons, they also don't couple. And sometimes the research scholars, they get the shock of their life when they, especially when they work in nucleosides, that 2 nuclei, 2 hydrogens which are related to each other by 3 bonds, and each of them are showing singlets, or means they are not behaving in any way that they are able to see that other hydrogen which is 3 bonds away, because the dihedral angle is 90. The moment the dihedral angle between those is 90, it doesn't matter that they are 3 bonds away. So that means it is due to the intervening, the bonding, the efficiency of the bonding and the efficiency of the overlap. So in the case of trans, the efficiency of the bonding overlap is much, much higher as compared to the cis. So that is why you have trans more than cis, but only in rigid alkene systems, not in alkanes. In alkanes, J cis can be higher than J trans. Again, the answer lies in the dihedral angle. That is the short answer. Otherwise, you see the factors affecting coupling constant. That is another, you see, at least 30 minutes of the talk. So because in 2 hours, you have to choose the basics. So you cannot, you see, it's a full semester course. So we take 20 hours to teach NMR, and then condensing it, distilling it in 2 hours is only to clear your basics. But this is based on the factors affecting the coupling constant. Hope that it makes sense to Arshdeep.
Thank you, sir. So one more question.
Yes, please.
Sir, in these slides, we have seen that you have said area under the signals is directly proportional to the number of protons. But if, sir, we compare the signals in which we have 3 CH3 identical groups, and if we have 1 CH3 group, definitely area of 3 CH3 groups is higher than the area of 1 CH3 group.
Yes.
So, sir, height is also dependent on the number of protons, no?
No, height is not dependent. You see, height is a unidimensional. Please remember, height is a single dimension, has a single dimension. Area has 2 dimensions. What you do, you just try to draw a broad signal, which is very short, but its base is very wide. the area under that peak would be much higher as compared to a peak whose area is so short, but it's so tall. So it is the area under the peak which is important and not the height. Although what you are saying, almost 90% of the times, the peak which has higher area might also have the higher height, but that would set a wrong fundamental in your mind if we say compare peak heights. We cannot compare peak heights. It is only the area. Hope that, is that okay? Or you need still more elaboration?
No, sir. It's okay. Almost clear.
So
Thank you,
you
sir.
you are a bachelor, master, or a PhD student?
Sir, I am in BSc 5th sem.
Oh, good. Great to know. I can see some students are joined from Ujjain also, because they asked me at that time. There are some Rachna Sharma from Ujjain, Vikram University, Ujjain. I can see there's some. Yes, please, Namita.
Hello,
Yeah,
sir.
Namika, you asked that question yesterday.
Yes, sir.
I remember.
Sir, I want to ask that you are saying that height doesn't matter, but we have studied that exchangeable protons are broad and their height is very less.
Mhm. Yes.
The spectra is very less. So height depends upon some factors. Sir,
First of all, exchangeable protons, that's what I say. You see, it is good that so many questions are coming. Namika, even exchangeable protons, they need not necessarily be broad. If you take a pure sample of ethanol, right, in DMSO, the OH would not be a broad singlet. It will be a clear triplet, as sharp a triplet as that of CH2, right? So the broadness is only because the more the exchange, more broad they are. But I'm saying do not confuse between the height and the area. We can never compare heights, because basically what is happening, it is the area under the peak which would be equivalent, which would be proportional to the relative proton count. Another thing about which I don't know if you paid attention. I'm screaming hard to say it gives us the relative proton count and not the absolute proton count. That's a different story, that your relative proton count may be the same as that of your absolute proton count. But it gives you the relative proton count. That means your absolute proton count would be equal to the relative proton count multiplied by x, where x is an integer. It can be 1. When x is 1, you have the relative proton count as equal to the absolute proton count. So Namika, height is immaterial, whereas at the same time, as I earlier said, in 90% of the times, the height of a signal which is having more number of hydrogens, in 90% of the times would be more as compared to the other signal which is having less number of hydrogens. But that is not a foolproof way, because height is immaterial. Height, you see, if your singlet, if your compound is so pure, then the singlet would be such a tall singlet that it would be just like a line. And your doublet can have a broader base. The broader base may not necessarily be due to exchangeable. It can be due to splitting also. So that is why do not confuse between the height and the area. It is always the area. And you people are fortunate enough, you do not have to measure the area. The NMR, if you look at the NMR spectrum, the computer automatically measures the area and then do this relative proton count and write it under the peak, right? So if you would look at say 5, 10, 20 different NMR spectrum, I think it would be clear to you that we cannot compare peak heights. Yes, Namika, okay?
Sir, I have one more question.
Yes, please.
Sir, I have one more question.
Yeah, go ahead.
Sir, we are saying that proton is spinning and it is charged. So it is producing a magnetic field. So that magnetic field is going to interact with the external magnetic field. So what about neutrons? Neutrons are uncharged, or so although they have spin, then how they are producing the magnetic field means they are uncharged.
Okay. Where the neutrons are.
The
Where
nucleus.
they are in
Sir, in
the
the
they are in the same cavity. They are in the same center. They are in the same room. They are in the same storage space.
yes, sir.
Right? So when we calculate the spin, you see the charge is only on the, we are talking about the charge on the nucleus. Do not confuse between the charge and the spin. Nucleus, the neutron is not charged, but it is having a spin. The charge, the magnetism is due to the proton. And we say the nucleus is spinning because proton, the neutron is not spinning separately. It is not outside the nucleus. It is in the same nucleus. So the spin is determined by the number of unpaired protons and the unpaired neutrons. Clear? There is no doubt about it.
Yes, sir.
Right? But when it comes to the spinning charge, whole of the nucleus, what would be the charge on the whole nucleus? It will be positive.
Yes, sir.
And whenever you spin a charge, there would be a magnetic field associated with it. So I can give you a theoretical answer. Suppose you take the neutron out, still the nucleus would be positively charged. And suppose you add 2 more neutrons, still the nucleus would be positively charged. So the neutron's contribution is towards determining the spin, not towards the charge. Right?
Okay, sir. Yes, sir. Thank you, sir.
Excuse me, sir.
Yes, please.
Sir, yeah, I want to ask on this question only. After that, I will ask some question from that YouTube only. We know that proton is spinning. It has a charge and it produces the magnetic field. It is having 2 poles, north and south. So in basic physics, we have studied that when anything is kept in revolving magnetic field, external magnetic field, it also acquires some poles. It means that if protons are spinning, they are producing the magnetic field. Neutrons are close to the protons. Why can't we say that protons are also producing neutrons are also producing magnetic field influenced by protons? Can we say that, or is this happening there in the nucleus?
Number one, I'm not competent enough to answer this basic fundamental question. That's the one thing. But with the limited knowledge that I have, I do not think that we can say that the neutrons would acquire a positive charge due to protons. If that would have been the case, the neutrons are always there spinning along with the proton. What we are doing by putting it in an external magnetic field is only aligning them with or against. That's the only thing we are doing. We are not generating an additional charge. So there is no need of inviting an external magnetic field in this question in order to answer whether the neutrons would acquire some charge or not. So there would be inherent charge already due to the protons if what you are saying is right. But with my limited knowledge, I don't think that the neutrons acquire any charge because that is a fundamental property of the proton, neutron, as well as the electron, that what is having with charge. Right?
Okay, sir. Okay.
I don't know. Did you?
Yeah, I got.
Did you attend my yesterday's lecture?
Yeah, sir. Yeah.
Okay. So because I tried to throw a light on it, that how do we determine this, the spin I, right?
Okay. So from YouTube, we have some question. The first question from Rajat Sharma. He's asking that why don't all the nuclear spins simply fall to their lowest energy states to minimize the total system energy?
They always are in the minimum energy state. We are only creating an exalted energy state. That's the main difference between NMR spectroscopy and any other spectroscopy. You see, the atoms exist only in their minimum energy state. So they are in their minimum energy state. We are only creating this energy difference by the application of the applied magnetic field. For that, yesterday we said, if we do not apply an external magnetic field, then the energy, all particles, they would have the same energy. All nuclei would have the same energy. They would be randomly ordered. So by applying an external energy, only then due to m is equal to 2i plus 1, so hydrogens would have two orientations, low energy and the higher energy. So they are always in the low energy state. We disturb them first and then measure that energy difference. That's what we are doing.
Yeah.
Hope that the Rajat is listening to it.
Okay, so we have one more question, and the question is, besides proton, two more nuclei we are studying by NMR spectroscopy, that is 31p and 13 carbon. So basically, what all three isotopes have identical nuclear spin, that is half. So it means that when placed in external magnetic field, will they have difference energy in a different energy state? Will be same in each isotope, or will they have two discrete measurable energy states? Actually, I also
the answer lies in the magnetogyric ratio. Whosoever asked this question, ask the person to go to the YouTube, listen to yesterday's lecture where I came to the basic NMR equation, nu is equal to gamma B0 by 2 pi, and try to have, and I said the magnetic field associated with a nuclei depends on the magnetogyric ratio. So all three are identical, but all three have a different magnetogyric ratio. That is why we have different techniques, P31, 19F, carbon 13, 1H. That is why we have different, right? So the answer lies in the gyromagnetic ratio. Please refer the student to my yesterday's lecture where I gave a diagram, where I gave a table, or the table is available in the PEVIA, but I gave the basic NMR equation only to answer these questions. Nu is equal to gamma B0 by 2 pi.
Yeah. Thank you for addressing the questions, sir. So these were the questions from YouTube, and now the questions are open to Zoom audience. If anybody wishes to ask any question here from Zoom.
Most welcome.
Hello, sir.
Ma'am, one you are muted. I think we have some question from Rachna Sharma.
Okay.
Hello.
Yeah. So,
Sir, this is Rachna Sharma from Ujjain.
Yes, Rachna.
Sir, I have one question. Actually, I am working over the synthesis of nanoparticles, and for that I have analyzed my sample with NMR from Saurashtra University. Sir, they have just given me the printout of the NMR, and there are certain chemical shift value along with the type of hydrogen which is available. So in that they have given 3.9 to 3.6, and in front of that 11H and small m. Sir, what does this m means? Is it meta hydrogen? What is that?
What is there?
Sir, the chemical shift value is 3.9 to 3.69.
Last part, you have got a printout. Okay,
Yes,
that printout would look like the spectrum I showed you, an A4 size paper, which.
Yes, sir. Yes, sir. And there is a table in which the chemical shift value and the type of hydrogen is mentioned. Hello.
Okay.
So, sir,
Yes,
in that,
yes, I am listening you.
Yes, sir. So, sir, in front of that chemical shift value 3.9 to 3.69.
Yeah. So what is written in front of it?
Sir, 11H means 11 hydrogen and comma small m. What that m means? Small m. I don't know what is that.
No, but other than m, what else is written?
Sir,
other than m, is there written some D? Yes.
No, sir. No, sir.
Or
only small m is written. That is why I am getting confused.
You see, first of all, normally the output is never given in the form of a table. It is always either an FID or a printed NMR spectrum. But what you are saying, you see, I'm only hearing you. I'm not able to see the spectrum. Most likely it's a multiplet, and that you can see.
Sir.
But still, you
Yes, I
see, because I didn't see it, because it's the first time I'm hearing that some university or some institute is giving you a tabulated output, because we never
Yes.
give a tabulated output
Huh.
when we run an NMR. We always give an NMR spectrum, either as FID you process on your own, or a processed NMR, that's all. Because the operator doesn't know that what the NMR, what sample the NMR, whose NMR the operator is taking. Operator doesn't know what is there. So in all
Yes.
likelihood, it should be multiplied, but still, you see, I cannot be sure without looking at the data.
Yes, sir. You
without
said
looking
11 additions are given. I think it is multiplied. And M is for multiplied, I think.
Yeah, so then you can see it in the spectrum, because they gave a table. Along with that, there would be a spectrum also. So if that spectrum is showing a multiplet, the multiplicity is not
resolution is
symmetrical.
not so clear. That is why.
Okay.
Okay, sir. Thank you,
So
sir.
hope that that's all I can offer you, Rachna. And
Yes, sir.
it's nice that the people from Ujjain are here. Thank you.
Thank you, sir.
Thank you.
So anyone else? So dear students, I think you must have noticed in Professor Sharma's CV that he is the only person who visited Antarctica from Haryana, and I think from Punjab also. And how many people are from India have visited Antarctica actually? Professor Sharma, do you have some idea?
From Punjab, Professor Sandhu from Punjabi University, Patiala.
Yeah,
I know of that
remember.
person. He has visited. And from Chandigarh, there was one Dr. Vilku who has visited. So to my knowledge, to the best of my knowledge, from North, only these two scientists and one doctor, to the best of my knowledge. I don't know, because when you go there, there is a full roll where the names are in the golden at the station. They are there. So to my knowledge, there are 3 scientists from this area, one from Punjab, one from Haryana. And about Haryana, I'm very sure, because whenever the next person would go, I would be in touch. So that is the Antarctic fraternity. So I know that I'm the only one but from Punjab, there is one person, Dr. Sandhu from Punjab University.
Yeah, actually, now I remember that I met Professor Sandhu also. I met Professor Sandhu, and he showed me some pictures of the Antarctica, and you also must be having that. And I think Professor Sandhu,
I have a
he used to
lecture on.
Yeah.
I have a full
So
lecture on Antarctica.
Yeah, you can deliver a full lecture on your visit of Antarctica. Actually, that is
all
very
my own pictures, not from the Google. So those are like not when I visited it, these are not on the digital camera, so they are on the still camera. So I preserved, I got them digitized, and I have those pictures, because those are forever, I would say, with me. Rare pictures.
So, dear students, you can see that how versatile your teacher is, who just delivered you 2 lectures on basics of NMR spectroscopy. So he is adventurous, just like you. So, Yatin, do we have more questions?
From YouTube, it is clear there are no more questions, and from Zoom, I can give one more announcement. If anybody wishes to ask some questions, can ask.
So I think you will be preparing a video today and uploading today on the YouTube this lecture.
Yeah, this will be uploaded automatically when this live stream ends.
But please share the link with me. I couldn't find yesterday's, so please share both these links with me also.
Sure, sir. I will forward it to Vandana and sure.
Yeah. So I will be forwarding it to Professor Sharma. So if there is no more questions, so I think let us thank.
Excuse me, can I?
So yes, please, sir. Dr. Joginder Pal, please.
Yes, sir. Good evening, sir. I am Dr. J.P. Kukreja. I am from ONGC, and people from our organizations have also visited Antarctica. That's I want to bring it to your knowledge.
Oh, yes.
And I am very happy and very delighted and enlightened by your lectures, although I did my BSc in 1976. So, but due to this technology, I could get entry in your class, sir. So I'm lucky enough, and I was very delighted with your lectures, and uh, got my this NMR tech, which I have read long back, got it revised, sir. Thank you very much, sir.
Thank you. Thank you for attending. My pleasure.
So, Professor Sharma, so you must have noticed at how widespread the impact of your lecture is. And I am also very happy. I am also very happy that wide spectrum of people have attended the lecture. And UG students, PG students, and I told you that research scholars, they are also there. And many research scholars requested me to pass on the link, because they were not able to register them. So I'm very happy that CRSI has done a good job by inviting you to delivering a lecture, and we are highly thankful to you for accepting our invitation. And we hope that we will keep on troubling you in future also.
No problems.
And in the So thanks again. So I'm thankful to you on the behalf of CRSI, on the behalf of students, on the behalf of Guru Nanak Dev University. So we are thankful, and we will send you the link very soon. Thanks
please.
again.
I'm thankful to you, Professor Vanna, for giving me this opportunity to interact with the participants. And I would also like to place on record my thanks to CRSI, because they have bestowed that bronze medal on me. So I think that that was my duty to come to that. And on top of it, you see, I can't say no to Professor Vanna. And I was already, as I said, that I was a little bit inimical that last time I couldn't come. So thank you very much. And given mutually agreeable dates, I think that professors, that's the only job that they can do, that they can, if we can simplify things for the students, I think that's the best we can do. And the technology is making it easier. Otherwise, it would have been difficult. Even if you would have invited me to GNDU, then the students of Amritsar would have been there. And now you see, I'm happy to see a broad spectrum from all over India. So thank you very much for providing this platform. And thanks to CRSI once again. And thanks to Professor Vanna for all that arrangements. Thank you.
Very true, very true. And thanks to all the participants for joining and for the good interactive session. So see you soon at some place, Professor Sharma. Till then, goodbye. And goodbye to all of you. All the